When you write code in languages like C or C++, you hit an immediate physical barrier. Hardware and operating systems speak completely different native languages. Compiling that code generates an executable file, like a .exe for Windows, that is permanently locked to a single specific environment. If you try to run that exact same executable on a Mac, the system cannot read it. Java sidesteps this hardware lock-in through a design principle called write once, run anywhere. The language was intentionally designed so that environmental portability takes priority over raw, direct-to-metal computational speed. This flowchart illustrates how Java solves the lock-in problem by inserting a universal translator between your code and the hardware. That universal translator is the Java virtual machine. Notice how the middle step branches out. The exact same bytecode is being fed into 3 distinct JVMs, one for Windows, one for Linux, and one for Mac. To understand how this works in practice, we are going to map out Java's 2-step execution pipeline, define the software hierarchy required to run it, and examine how this system enforces strict structural logic on your code. To write reliable Java, you must first understand the exact engine that interprets it. Looking at this center flowchart, we trace the first step, compilation. When you finish writing a program, you run it through the Java compiler. Unlike a C++ compiler, Java does not output machine code. Instead, it converts your human-readable text into a .class file. That .class file contains bytecode. Bytecode is an intermediate, highly optimized set of instructions that contains absolutely zero operating system-specific logic. Because it lacks those OS-specific instructions, the host computer's CPU cannot read or execute bytecode directly. That makes the compiled file entirely useless without a dedicated software layer sitting on the host machine ready to interpret it. This diagram maps out that software layer, the JVM. This is step 2 of the pipeline. The bytecode enters through the class loader and moves into the execution engine. Here we encounter a necessary paradox. The bytecode is completely platform independent, but the JVM running it must be platform dependent. You have to install the specific version of the JVM built for your exact operating system. That is because the JVM's primary job is to take that universal bytecode and translate it into the specific native zeros and ones that your local hardware requires, doing so actively at runtime. While it translates, it also acts as a sophisticated manager. Looking at the memory area section of the diagram, the JVM automatically handles data allocation in the heap and stack and continually runs garbage collection to free up unused memory. The JVM acts as an abstract, virtual layer between your program and the hardware. By stripping away direct pointer manipulation and verifying every block of bytecode, the engine forces the code to operate within a strictly defined memory sandbox. The JVM does not sit on your computer by itself. It exists inside a strictly nested software hierarchy. At the very center is the JVM, which we know is strictly the execution engine. Wrapping around that engine is the JRE, or Java Runtime Environment. The JRE contains the JVM, but adds the core class libraries like java.lang and java.util that provide the basic files necessary just to run an existing Java application. Wrapping around the JRE is the JDK, the Java Development Kit. This outermost layer includes the execution environment, but adds development tools like the Java compiler and code debuggers. If an end user simply wants to play a Java game, they only need the JRE. But if an engineer wants to build that game, they require the entire overarching JDK environment. Because the JVM is such a rigid execution engine, it forces developers to structure their code in highly predictable ways. We can see this in how Java handles object-oriented programming. This code snippet shows inheritance, where a child class, like dog, acquires the properties of a parent class, animal, but using the extends keyword. But look at the multiple inheritance diagram here on the bottom left. If a child class tries to inherit from 2 different parent classes that share a method name, it creates an architectural ambiguity known as the diamond problem. Java simply rejects this concept. Classes can only have one direct parent class. To maintain flexibility, Java provides a workaround. This diagram shows how a single class can implement multiple interfaces. Interfaces act as structural contracts rather than executable code, safely allowing multiple inheritance pathways. Java enforces single inheritance as a deliberate architectural boundary. It guarantees the JVM will never encounter an ambiguous execution path at runtime. Tracing the entire lifecycle puts these pieces together. A developer writes an object-oriented class inside a .java file, relying on the tools provided by the JDK. During the build step, the Java compiler converts that high-level logic into universal bytecode. That bytecode is deployed to a target machine, where it pulls from local JRE libraries and is ingested by the JVM. As highlighted in this text definition, final execution happens through runtime polymorphism. The JVM dynamically resolves all object-oriented relationships and overriding rules in real time, translating the bytecode into hardware-specific output. This strictly separated, layered pipeline is exactly what generates Java's operational consistency across different systems. The ultimate engineering trade-off of Java is clear. It sacrifices the raw execution speed you get from direct-to-metal compilation and pays that cost to guarantee environmental portability and automated memory safety. That specific trade-off is the reason it remains the backbone of complex, large-scale enterprise systems around the world. Writing robust Java code requires aligning your syntax with the architectural logic of the engine that brings it to life.